This tutorial will show how to model a mat foundation that supports a wall with an overturning moment. The mat is 1.5 meters thick, supported in its entirety by soil springs. The only loads on the model are the self-weight dead load of the mat and the overturning moment on the wall. This model will be constructed using kilonewton meter units and will be started from scratch without the use of templates. It will have 5 grid lines in the X direction and 4 in the Y, with spacing of 6 and 5 meters respectively. A double left click on the grid allows us to modify the spacing, and we will alter the X grid to move the last grid line to 22 meters. Next, we will define a slab property to represent the mat. We will name this new property mat and select a type of mat from the drop-down list. We will enter a thickness of 1.5 meters and also select the thick plate option as we wish to include shear deformation. Now we will draw a rectangular area object to represent the mat by dragging from grid A4 to grid E1. For the rest of the model, we will work without the crosshairs on the pointer. Click on the Select button to leave the draw mode and right-click on the mat object. This brings up the object information form, where we will extend the mat in every direction by 0.5 meter. The next step is to define a beam property that will approximate the stiffness of the wall. We will use a beam object to model the wall. For this case, we will add a rectangular beam, which we will call wall, that will be 0.3 meters wide and 3 meters tall with no self-weight. We will click on the No Design option as the wall should not be designed using beam procedures. Next, click on the Draw Line Objects button and select the property of wall in the Properties of Object box. The wall will span one bay from grid C to D. We will now add the soil supports. Select the mat object. You can verify your selection in the lower left-hand corner and go to the Assign Soil Supports command. We will use the default value of soil 1. The geometry of the model is complete, and next we will define the loads. We start by defining our load cases. We will rename the default case to DL for dead load, which has a self-weight load, and we will add an earthquake case. Next, we will add a null point object with no properties to the midspan of the wall. This is where we will apply the overturning moment. Select this new point object and go to the Assign Point Loads command. Make sure that the earthquake case is selected and apply a moment of 20,000 kilonewton meters about the y-axis. It is important to note that nonlinear uplift iterations work only on load combinations. You must have load combinations defined prior to doing the analysis if you wish to consider uplift in the soil-bearing springs. We previously defined 2 load combinations specifically for soil-bearing uplift. Uplift 2 with 0.9 times the dead load and -1 times the earthquake load will be the governing case for our analysis. The last step before running the analysis is to set the analysis type to iterative for uplift from the set options command. We can now start the analysis. The uplift analysis status box shows that the analysis for load combination uplift 2 was solved in 2 iterations. Note that combination decon 6 ran out of iterations while solving, but this is a load combination for the design of the mat and not appropriate for the overturning uplift check that we are performing. The deformed shape for the uplift 1 load combo is displayed on the left. However, it is load combo uplift 2 that we are interested in, so we will revise the display. In the right view, we will display the soil bearing pressures for this combination. Note how the soil bearing pressures do not go below 0, indicating that there is no tension in the soil springs. This concludes this tutorial.